Hello everybody, welcome back to our channel. In this episode we're going to be doing a physics 7C video, and my goodness, I did not believe that this was going to happen. It's been a hot minute since I've done a video, I know, but hey, things are changing. The world is very crazy right now, so might as well get this started. You guys like the videos, you guys commented on the videos, you guys share them, and now well, here we are. We're going to be doing physics 7C videos. That's what's going to be happening this quarter. So the topic for today is the one-dimensional wave, which is the first topic for 7C. So I thought, hey, it's been a minute since, it's been a while. So why don't we just start with a brief introduction to what the equations that we're going to be using look like. And then we are going to do like a very small, sort of like on the easy side introduction practice problem. Now, all of the problems that I do here on this channel, every single one, physics A, B, or C, are always past quizzes. So this isn't something that I just like look up on the internet. This is something that I get from the, from the repository, I guess, of quizzes from the physics department. So every single problem that we're going to do is a quiz. And for 7C, what I'm going to be doing is, if you would like to print the PDF of the actual quiz that was given to the students, it's the same problem, but the actual PDF, so that you don't have to write it. I'm going to be leaving a link on the description with, the link to the empty PDF, so that if you would rather just print those and then just like work on them, that's perfectly fine. So anyways, let's get started. So the wave equation, let's see. So the wave equation, let's just write it down real fast. T, and then we have A sine 2 pi time T plus minus, we're going to be talking about this in a second, 2 pi x lambda plus this little thingy plus y naught. All right, so this is the main equation that we're going to be working with, and then we also have two little auxiliary equations which are called the velocity equation, which is basically lambda over t, which is this lambda and this t, and then we have this other thing called a frequency, which is just 1 over t. So these are the three equations that you guys are going to be using, and pretty much every single problem that you are going to do for this part of the quarter is going to have to do with, this equation with the help of these two equations as needed. Now, what's the name of all of these things that we have over here? Well, A is the amplitude, and it refers us to like how, how big or how small your wave is. Then we have this thing, which is period, which is, the time to have like one full cycle. Then we have this thing, which is called lambda, and it is the wavelength. The wavelength is the physical equivalent of a period, and I will be talking a little bit more about this in a second. This thing here is called a fixed wave constant, not to be confused with the total phase. So if you add this plus this plus this, you get the total phase. And the total phase is different from the fixed wave constant. They are two different things. They are related, of course, because if you add this plus this plus this, then you get the total phase. But there's a reason why sometimes we, write the fixed wave constant with a little naught here, a little zero, and then the total phase, we do it with capital letter over here. And then we have the equilibrium position. And it basically refers to like if your wave is moved upwards or downwards, then the equilibrium position, you know, that's how you represent this over here. Now, in terms of this plus minus, if your wave is moving to the left, you're gonna have a plus sign over here. If your wave is moving to the right, you're gonna have a negative sign over here, basically. So this is basically the wave equation, and we're also gonna have, you know, for all of these quizzes, you have to get used to seeing these graphs over here. So we have basically two types of graphs. The first type of graph that we can have, so I'm just gonna, you know, draw a generic wave over here, is y of x at a time that's fixed. And then this is x because this is y of x, and then this is x. Now, the second type of graph that you guys are gonna see, and you know, this is, you know, if somebody's gonna mess up this, it's just by not recognizing that they are different things, but they are. So this is a y of t, but x is fixed. And this is y of t, so this is actually time. Now, this one's usually meters, and this one's always in seconds. But you know, the units don't matter. What matters is that sometimes you have y of x, sometimes you have y of t. Both of the graphs, you know, their core are just sine functions, so both of them look pretty much exactly the same. So the most important thing is, you know, what's up here, what's here, what's up here, what's here. And you know, the reason for this is that depending on the graph that you have is what information you're going to be able to pull from it. So now let's just do a little experiment over here. So amplitude is pretty easy to get from both of them. Amplitude, if you have any of these graphs, you will basically, you know, just see what this distance is, what this entire distance is, divided by 2, and then that would be your amplitude. So your amplitude would be, for example, this or this, right? So amplitude you can actually get from both. Period is very important because period is how many seconds does it take for your wave to, you know, go up and down and then up again. So your period you can only get from a y of t graph with x fixed. So your period you can only get from this graph over here, and it will be, for say, you know, this delta t would be equal to the period, but only from this graph over here. A lot of students would, you know, if they're only given this graph, then they would try to get the period from this, but this isn't seconds, this is meters, right? Wavelength, exactly the same, except we have the opposite case. So wavelength, you would go, say, from here to here, and then, you know, this is your wavelength versus this is your period. But your wavelength you can only get from y of x graphs, because a wavelength, you know, it's a length, and lengths are in meters, centimeters, you know, whatever distance measure you want to use, but certainly not seconds. So again, this is a very, you know, common mistake that students make. They want to get a period from here or like a lambda from here, and you just can't do that. Fixed wave constant. Fixed wave constant is usually the last thing that you're gonna get on any given problem, and the reason is because the fixed wave constant you usually get from the equation itself. So we're gonna, from the equation, usually, if you have a very good eye, you might be able to, you know, infer it, but personally, I don't really have that good of an eye, and I've been doing this for 10 years, so, all right. And then equilibrium position, you can get from both. You can get it from the graph, you can get it from the equation, but the easiest way is just to get it from any graph. Both of the graphs have the same equilibrium position because this is the same wave. So you can get it from both of them. This one's pretty easy, just as much as amplitude. And then left or right. If you only have these two graphs, then you have to use both of them. You have to use both of them because you're gonna, say look at a position, and then you can get maybe a time derivative of this, and we're gonna be working with this. But left and right, whenever possible, you have to use a combination of both. Otherwise, maybe the problem itself is already telling you that also happens, but you have to use both. So anyways, let's just start with a very easy, introduction practice problem, which I'm gonna show you on the screen right now. So the problem statement says a one-dimensional sinusoidal wave is moving to the left at a speed 2 meters per second at time t is equal to 0. You take a snapshot of the wave, and then you get the following picture. The picture, I'm going to show you a big image of the picture, so don't worry about it. What is the period of this one-dimensional wave? Write down an equation to describe this one-dimensional wave, and then we actually have to make another plot. So let's see. So right now I'm going to show you, a bigger picture of the wave, which I'm going to be doing for this entire module because the pictures are so important. Again, if you would rather have the PDF, the link is going to be in the description. But let's see. So feel free to pause it if you need to. I'm just going to move on. So as you can see, I have, a little drawing of what we're going to be working with. And the first thing that we have to find is the period. Okay, so the first thing that we need to check out is that this is a y of x. This is y versus x. So if I use my little method, when I just look at crest to crest and then I just figure out that distance, that is not going to give me my period. That is going to give me my lambda. So, that's going to be useful in a second, but not for the period. However, I do have my velocity over here, and this is where my auxiliary equations are important because I have this equation over here, right? So this is, I'm just going to copy that. B is equal to lambda over t. So basically, I have the velocity. If I find lambda, then I'm going to be able to find t, correct? So let's see. So if you go back to the graph, which I'm going to put back on, in order to find lambda, you have to basically, go from either crest to crest or minimum to minimum, just whatever full cycle you have, and then go from here to here, and that is going to give you your lambda. Now, in terms of the graph, this isn't so obvious over here because I just copied this thing and I did my best, but it's still not obvious. But if you actually look at the original graph, the graph is divided in thirds. So if you just count 1/3, 2/3, 3/3, 4/3, 5/3, 6/3, then you're gonna see that your lambda is actually 8/3. Again, the graph from the original problem is divided in thirds, so you would go 1/3, 2/3, 3/3, 4/3, 5/3, So now we have this lambda, and then we have a velocity of 2 meters per second. So basically, my period, which is my final answer for A, is going to be lambda divided by B. So it would be 8 thirds divided by 2, and then 8 thirds divided by 2 is equal to 4 thirds of a second. Final answer. So final answer, this guy is also going to be useful. So now let's just move on to part B. So part B is write down the equation to describe this one-dimensional wave. So we need the entire thing. You know, I'm just gonna copy this real fast over here. A sine 2 pi t plus minus 2 pi x lambda not plus y. Okay, so this is the full equation and we basically have to fill in all of the blanks. Amplitude, so let's see. Amplitude is basically the entire, you know, distance from top to bottom divided by 2. So in this case, the maximum is +1 and then the minimum is -3. So 1 plus 3 is 4 divided by 2. Amplitude is equal to 2, and then this is meters, so amplitude is 2 meters. Now we have this one. T we already have, so it's 4 thirds of a second. Lambda we already have, so lambda is 8 thirds meters because we got it from a meters graph. This little guy over here is going to be the last one that we get. It's usually always the last one. And then y naught is, you know, how move this thing is. So if amplitude is equal to 2, but then my max is at 1, then that means that it was moved 1 down. So y naught is actually equal to -1 meters. So we have everything that we need except for this little guy, and how you get it is because you have everything else at this point, you would basically substitute any point here and everything else, and then you would just find it. So say for example, if you look at the original graph, what's a very easy point to find? So just by looking at a graph, I can see that at point when x is equal to 1, at t is equal to 0 because it's equal to 0. So I'm looking at this point over here, by the way. Y is equal to -3. So just by looking at the graph. So I'm going to put this over here. So y is equal to -3. And this is equal to 2 amplitude sine 2 pi time, in this substitution is equal to 0 divided by 4 thirds, but this is all 0. And then, we didn't do this. So is this left or right? This is left. So left is equal to plus 2 pi 8 thirds. Oh no, this is x, so x is just equal to 1 divided by lambda, so 8 thirds over here, plus y naught minus 1. So let me just rewrite this. So -3 plus 1, so this is equal to -2 divided by 2, I'm dividing this, is equal to sine of 2 pi times 1 divided by 8 thirds plus 0. So sine inverse of -1, this is just -1, is equal to 2 pi times 3 by 8 plus this constant. And if we do this, then we'll see that this is 3/4 of pi. feel free to do it on your calculator. I should go get mine soon. But I've done enough of this that I just know my unit circle. But this is your 5. And this is basically how you're gonna get your, you know, your phase, your fixed wave constant every single time. It's always gonna be the last thing that you get. And so that's basically how you get it. You substitute everything else, and then whatever you get it. So now part C says, on the graph below, plot yt for x is equal to 3. So let's just put a little graph over here at the bottom. I'm running out of space, but this is enough. So let's see. So we're gonna do this, and then say this is 1, 0, minus 1, minus 2, minus 3. This is gonna be time, and what they want is y of t at x is equal to 3 meters, like this. Okay, so amplitude is gonna be the same because these two share amplitudes, and then these two also share the y naught over here, so this is also gonna be, you know, removed. So my maximum is gonna be over here, and my minimum is gonna be over here. I don't have to do anything except just look at this graph, because even though this is, you know, y of t and this is y of x, this is the same wave, so they share that information. What they don't share is that this is lambda and this is t. So in order to do a full iteration, so in order to do this on your, you know, original sine function, these two crests should be at 4/3 of a second. However, we need to recalculate this fixed phase constant, because what we need to do is that we can't use this entire equation, because this equation has t and x unfixed. So what we need to plot is not necessarily this equation, but we actually have to substitute, right? So let's just substitute. So if I substitute, I'm gonna get, so this is gonna be y of x is equal to 3 time unfixed. So this is 2 sine of 2 pi t 4/3, and then this is fixed, so this is plus 2 pi 3 meters. And then we have our lambda, which is 8/3, so 8/3 over here, plus, what was this number, 3/4, and then minus 1. So this is actually what we have to plot. So the only thing that I need is to add up these two numbers over here, because the addition is gonna give me, you know, how much should I move this way to the left or to the right. So let's see what we can do over here. So this is 9/18. So this number is 3, that's a 9, then that's a 10, and then this is 3/4. So what do we have over here? Oh, and we're adding them. So this is 6, 8, 18 plus 6, 24, and then 24 divided by 8, that will be equal to 3 pi's. So we need to move this by 3 pi. Now, if you remember your unit cycle in your original, you know, sine function, this is, you know, I'm just gonna So this is your original thing, right? And then, you know, this is pi divided by 2, this is pi, this is pi. So let me just do this over here, like on a bigger scale, so you guys can see, because, you know, you're gonna be doing this a lot. So your usual sine function always starts, you know, going up. Like this. And then you just do halves. So this is 1/2, 2/2, 3/2, 4/2, 5/2, 6/2, 7/2, 8/2, 9/2, 10/2, 11/2, and then this is all pi, right? So this is pi, 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 da, 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 and there we go. All right, so this is how it goes. It's all halves. Of course, 2/2 is just 1, 4/2 is 2, and so on, but this is how you can pretty much divide it pretty easily. Now, in this case, I got 3 pi over here as a phase constant positive. So that means that, oh, and of course, if you go towards the negative side, then you do -1/2, -2/2, -3/2, and so on, right? So this is positive, so I just drew the positive side, and I got 3 pi, so 3 pi is actually this number over here. So that means that instead of, you know, starting my graph over here from like going up, my graph actually starts over here. And then, so it actually starts going down like this. So that's gonna be my final answer. So my final answer is gonna be, you know, just something like this. And now, you know, the phase constant is correct, the amplitude is correct. The only thing that I have to do, this is my amplitude, this is my phase constant, is just put some numbers in here. So a full, you know, iteration should be, what is it, 4/3. So this is 4/3 like this. And yeah, you know, that's it. If I had done like another iteration, that I would do 8/3, but you know, I did like a very small graph. So this is the best that we can do. This is a full final answer. So this is a full final answer and a full introduction to this particular topic. You know, again, the only reason why we're doing this because you found them so helpful. Problems, are they gonna get way harder than this? No, I don't think so. But you do need a lot of practice. So even though this problem was, you know, relatively, you know, plug and substitute, we did learn a lot of very useful things. Especially, you know, t goes with t, x goes with lambda. If you wanna mix them up, you do them through this equation. And then we also learn how to do a little graph. We also learn how to position our graph so that it's okay. So I think that this was a very productive problem. So anyways, this is the end of the problem. If you guys, you know, like this video, if you would rather have, if you want me to do more of an introduction sort of video instead of just problems, let me know. Again, the only reason why we're doing this is because you guys wanted it so bad that the department was like, you know what, we're gonna put you on this for this quarter. So I'm super grateful for that, and I'll see you guys on the next video.